This talk is motivated by a discussion that we had in the 2023 PI meeting in, I think, 2 floors up, with the NSF program officers. And the program officers asked what are the areas of mathematics that are potentially very impactful for machine learning, but have not yet been explored that much. And the answer from the PIs was maybe mostly they said that algebra was one of the areas that could be used in the theory for machine learning. And just I want to give you some not overview, but just like maybe some snapshots of how we can use algebraic techniques to design and analyze machine learning models, just in a simple, through some examples. So I'm not going to cover the entire things that you can do with algebra in this talk, just a few examples that are maybe biased towards the things that I've been thinking about. But here in the audience, we have a lot of experts on these. For instance, Lindsay, Catherine, and Elisenda work on things related to the learning landscape via algebraic geometric tools. There's some work related to category theory towards the formalization of algorithmic alignment that is related with Joan's work in geometric deep learning. And there's a lot of work that have to do with the exploiting symmetries in the architecture design. And here we have a lot of experts in graph neural networks and algebraic neural networks, and also equivariant machine learning, like Robin and Luana and Alejandro, and I'm sure that Alejandro will talk about it later today. So in machine learning, I can think of like 3 types of symmetries, or maybe there are more, but just maybe you can tell me what other symmetries you can think of. But from the physical sciences, we have the passive symmetries and the active symmetries. The active symmetries are the symmetries that the physical law obeys. Like say, if you have a protein folding problem, this problem is rotation equivariant. Those are symmetries that have to do with like the physics and the conservation laws that the physics satisfy. There's also the passive symmetries that have to do with the fact that when I have some object, mathematical object or physical object, there's not a unique mathematical representation of it. There are many ways to represent it in different ways, using different coordinate systems, different unit systems. And those symmetries are the passive symmetries that is just have to do with the fact that there's not a unique way to express objects, and that gives you an equivariance by design. And then there's also the symmetries that arise in these very sophisticated deep learning architectures where your space is very over-parametrized. And so there's not a unique correspondence between parameters and functions. There are many set of parameters that design the same functions. And so if you're going to use these weights of machine learning models as a data modality, so for instance, if you're going to do fine-tuning, if you're going to do transfer learning based on the weights, like people do with like large language models, then if you're going to work in this parameter space, then you have some symmetries that you may want to exploit. So as an example, I'm going to tell you one passive symmetry, which is the symmetry of graph neural networks. So if you have a graph, you typically represent it as an adjacency matrix. And there are many adjacency matrices that represent the same graph. Just permuting rows and columns give you an alternative representation of the same graph. So all graph processing methods, like spectral methods, are equivariant with respect to this symmetry. And of course, you want to implement this symmetry. There's no graph processing method that I know of that doesn't implement this symmetry. And this is a huge symmetry because it's n factorial, the size of the permutation group. And there's explicit computations that tell you how much do you gain in terms of sample complexity and generalization error by imposing these symmetries into your machine learning models. So that's one example. So in this talk, I'm going to give you some basic, just a basic idea behind more sophisticated algebraic tools. So I'm just going to give you the basic idea of how these algebraic tools, and then how we apply them to specific machine learning applications. So I'm going to explain you how we can use invariant theory, or a basic idea in invariant theory, to implement self-supervised learning that is equivariant. I'm going to tell you basic ideas from Galois theory that allow you to design invariant machine learning models on point clouds. And I'm going to tell you just an epsilon idea of representation stability that can be used as an inspiration for the design of any dimensional models. So models that are designed independently of the size of the object. So for instance, graph neural networks, you can have a fixed set of parameters and can be evaluated on graphs of any size. So what are the underlying assumptions and mechanisms that allow you to do that? And if you have checked Yuxin's poster, she had a poster on this specific topic. So let's start with the equivariant machine learning via invariant theory. So imagine that we have this point cloud that is moving very, very slowly in the top right. We get there. So we have a point cloud, and we want to learn a function of this point cloud that is invariant with respect to the orthogonal group acting on all the points simultaneously. So if I have an orthogonal matrix applied to all the points, and I have a function that is invariant with respect to that. So for instance, the energy of this point cloud is invariant with respect to that. How do I parameterize the functions that satisfy this property? And this is a very classically known question or thing in invariant theory. The first fundamental theorem of invariant theory for OD tells you that a function is invariant with respect to OD, if and only if you can write it as in terms of the inner products of your input vectors. So that gives you a precise characterization of all the invariant functions for this group action. And you can have similar characterization for other groups. And I think in 2022, I gave a talk about how do you extend these to equivariant functions in this group, in this thing. But I'm not going to do that. I'm just going to tell you how we can use this to define equivariant contrastive learning. Equivariant self-supervised learning. So say, if you are familiar with the self-supervised learning framework, what you have is a bunch of images, and you want to represent them in Euclidean space. So maybe you want to represent them in the sphere, so that the intrinsic properties of the images are codified in the metric of the space that you embed them. So for instance, one way of doing this is via self-supervised learning, where you define a set of augmentations, so that are transformations of your image that they don't change the underlying content. So for instance, here you can make this cat more yellow and still a cat. And in this simpler model, what you do is you learn an embedding that is invariant with respect to these augmentations. So the augmentation of the image doesn't really change the embedding. So what we can do is extend this self-supervised learning to equivariant with respect to embeddings. So say, if I apply an augmentation to my image, the embedding doesn't stay invariant, but there exists explicit transformation that sends the embedding of the augmented cat to the embedding of the original cat. And this orthogonal transformation is the same for every image. So if I have a dog and I augment it, I know that the transformation in the embedding space is the same orthogonal transformation. So that gives you some interpretability on the space of embeddings. So you know how you need to transform your objects in the embedding space so that they come from a known transformation in your image space. And that may be desirable for interpretability purposes. Do you have a question?
Just out of curiosity, do you need to work in higher dimensions?
A higher dimension than the image space?
The space where you're embedding, does it have to be higher dimension?
It doesn't. It cannot be like the sphere of dimension 3 or dimension 2, but it doesn't need to be higher than the dimension of the image space. It can be lower than the dimension of the image space. So maybe like 128, something like that could work.
Dimension otherwise, without this invariant.
Yeah, and also this is not a group equivariance per se, because the set of augmentations do not form a group. They're just some transformations. So this commutative diagram is not really a mathematical commutative diagram. We're going to achieve this in an approximate way. And then we can extract some conclusions that if you can actually make it equivariant, then the set of augmentations will form a group, and it will be a subgroup of the orthogonal group, which is typically not the case. But if you have a finite group, you can put it inside the orthogonal group. OK, so the way you do that is by using this idea of the fundamental theorem of invariant theory that tells you that if you have two pairs of points and they have the same inner product, then there exists an orthogonal transformation that sends the first pair of points to the second pair of points. And so you can, and this is an if and only if. So you can write your embedding to satisfy that the inner product of the embeddings of your augmentations are the same as the inner products of the embedding of your original images. And if you satisfy that, you know that there exists an orthogonal transformation that makes the diagram commute. OK, so augmentations in the image space correspond to orthogonal transformations in the embedding space. So you can do that to write a small modification to the sim-clear objective, the standard self-supervised learning objective that is also written in terms of pairs of objects, like the self-supervised learning is. So that's a computational advantage that you have, that you don't have to write something that is more complicated in terms of representations of the group. You can just do it in terms of the invariants. And nicely, the invariants can be written in terms of inner products. And then you can just write your loss function for the self-supervised learning objective to be the classical self-supervised learning objective plus some term that penalizes how far you are from being equivariant, which is basically the difference between the inner product of the embeddings of your points and the inner products of your original points, the embeddings of your original points. And you can show that if you can make this loss term equal to 0 exactly, then there will exist an orthogonal transformation that makes the diagram commute. But in practice, it will be close to 0. And so if you can do that, then it means that the group of augmentations are a subgroup of the orthogonal group. Well, the group of augmentations that don't get killed to 0, because this result tells you that there exists an orthogonal transformation that makes the diagram commute. But that could be the identity. The identity is also an orthogonal transformation. And in that case, you would recover the invariance. But there's some reasons why you get something that is not the identity and that you make something that is equivariant. But maybe not, you don't, maybe there's some parts that of the group of augmentations that do go to the identity. Yes.
So from an implementation perspective, this loss requires to consider all pairs of points, which can be costly, while the theorem based on the rotation would just be based on points. Are there any advantages or differences in simply, instead of penalizing the equivariance loss that you have there, to simply penalize the error and optimize with respect to a rotation?
So for these laws, I mean, you write it in terms of pairs in the same way that you do the self-supervised learning. So when you have pairs from the self-supervised learning, like x and x prime, you have other pairs here, but you don't do it over all the pairs. You do it per batch. There's a simplification that makes it to be computationally reasonable. Yeah. Yeah, but that was an aspect that made the implementation a little bit tricky. That's true. By the way, I did not implement this. This was work that I did with the group of Stephanie Jegelka. This was implemented by Sharut, who is a student of Stephanie. And she's great. So this example here shows that if you have, shows how these equivariance to these augmentations behave. So if you take these images and you make them a little bit more yellow, and you look at the nearest neighbors in the embedding space, you get images that are more yellow. So it kind of illustrates how this behaves in the embedding space. Whereas if you don't, then you don't really see that transformation. Good. Any questions so far? So this gave you a small taste of how you can use ideas from invariant theory to modify some standard machine learning models to get them to satisfy interesting symmetries. So the next thing that I'm going to talk about is how we can use Galois theory to implement machine learning models on point clouds. And there's a lot of work in machine learning models on point clouds with applications to many things, chemistry, astronomy, material science. In my specific research for these machine learning models on point clouds, I came up with this problem in conversations with astrophysicists at the Flatiron Institute across the street. So they were looking to work on a regression problem on point clouds where they had an expensive simulation. This hydrodynamics simulation was an expensive cosmological simulation, and they had a cheaper cosmological simulation that was called the dark matter-only simulation. And so they wanted to learn properties of these point clouds that they would obtain with the expensive simulation from the cheap simulation. So it was like a regression problem on point clouds that was invariant with respect to orthogonal transformations and permutations. So how do we do that? So we have our points here, our endpoints in RD. This is my point cloud. And now I act by the orthogonal group on the left and by the permutation group on the right. So I want to look at the invariant functions with respect to that. So before, we saw that a function is OD invariant if and only if it's a function of the inner products. This is graph matrix, the matrix of inner products. And in order to implement the symmetry with respect to permutations, if I just multiply by permutations here on the right, then in the graph matrix, the permutations act by conjugation by permutations, so permuting rows and columns. So what the symmetry that we obtain here is the same symmetry as the symmetry of graph neural networks, where your graph is your graph matrix. That's the symmetry that I show you in the second slide. And so how do we implement this symmetry? We're not going to use graph neural networks. We could use graph neural networks and the graph matrix that would implement the symmetry. But we're not going to do that because the graph neural networks will require me to construct this n-square matrix, but this is a cosmological simulation. It has many, many points in dimension 3. So I don't want to go to something that is O of n square. We're going to be able to use these ideas from Galois theory and get them to O of n times d complexity. And also, I think that maybe this tool, this Galois theory tool that we use here, maybe we can use it for more broadly for other problems. I don't know. I think that could be interesting. And so the Galois theory approach says the following. So I have my group of interest, which is the group of permutations acting by conjugation in these symmetric matrices. And then this is a subgroup of a easier group to handle, which is the group of permutations of the diagonal elements and the off-diagonal elements independently. So if I have a permutation that permutes rows and columns, then it will send something on the diagonal to the diagonal and something on the off-diagonal to the off-diagonal. But not every transformation that you can write in this form comes from one of these forms. So this is a subgroup. And so the Galois theory framework tells you that the invariant functions with respect to the larger group are a subgroup of the invariant functions with respect to the smaller group. And there's this correspondence given by Galois theory. And so for this big group, the invariant functions are easy to write because it's just like permuting diagonals and of diagonals independently. So you can consider, for instance, the symmetric polynomials of the diagonals and the symmetric polynomials of the off-diagonals, and that gives you generators for the algebra of invariant functions for this larger group. So how do you go from the larger group to the smaller group? Well, Galois theory tells us that if we can construct a set of invariants that are only fixed by the small group and nothing else inside the larger group fixes it, then those invariants will generate the field of invariant functions. So we're going to get field generators for this group. And then there's another theorem that tells me that if I have the field, this Rochentlit theorem tells me that if I have field generators, then these field generators will be able to distinguish orbits, but not all the orbits. They will be able to distinguish almost all the orbits. There's a bad set that these field generators will not be able to distinguish. And this bad set is the zeros of a system of equations, polynomial equations. So this is like a small set. It's like an invariant measure zero set, unclosed. So that's what we are going to use. So basically what we're going to use is we know what are the generators of the field of invariant functions for the large group, and we're going to consider another element that is fixed by the smaller group, and nothing inside here fixes it, larger than Sn. And for instance, this object will do the trick. And so if I consider the field extension that considers the base field, added this extra polynomial, then the field that we obtained is the field of invariant functions for the group Sn that we cared about. So with these, we have field generators, and we can separate almost every pair of orbits. So that gives me, so now I have a characterization or like a formulation for the field of invariant functions for the group that I care about. And then I can turn, my goal was to write a machine learning model that was invariant with respect to this. So I'm going to turn this object into a machine learning model. So in order to turn this object into a machine learning model, I'm going to use an architecture that is called deep sets. That is a permutation invariant architecture. And basically, it's just that the reason why I'm going to do this is because these polynomials are not that well suitable for machine learning features, because polynomials of very high degree are unstable, and typically one doesn't use polynomials for machine learning, but you can use other things that have equal expressive power and that are better behaved than high degree polynomials. So this deep set architectures tells you that if you have a function that here is in our n elements in Rk, and you can write it, and this function is polynomial, is permutation invariant for the action of Sn, then you can write it as the composition of embeddings from each of the elements in your set, each of the n elements. You have a function phi that takes each of the columns of your matrix and then embeds it into a higher dimensional space. And then your function is going to be the aggregation of the sum of these embeddings of your columns. And there's some theorems that tell you like what is the dimension that you need to put here in order for this to be expressive. And the interesting thing about this machine learning formulation, that you write it like this, and then this embedding and this map you can learn from data using an MLP or something like that. The interesting thing about this formulation is that this is an invariant function that can be parameterized independently of the number of columns in your input. So it can be parameterized independent of the point cloud size. So this is something that you cannot do with a symmetric polynomial, because a polynomial is an object that takes n variables and outputs a function of these n variables. And if you have n plus 1 variables, you don't know how to evaluate that polynomial necessarily. But with this architecture, you can write it in a way that is independent of the number of objects in your input. So using this formulation, you can prove that the machine learning model defined as taking these deep sets of the diagonal elements and the deep set of the off-diagonal elements and the extra f star that we added using Galois theory, a function of these objects, these functions, will approximate any invariant functions on symmetric matrices with respect to the action that we cared about. So it's permutation of rows and columns. So this is a universal approximation result outside this bad set that is coming from the fact that we don't have algebraic generators, but field generators. Any questions or comments? Yes?
So adding the extra f star using the Galois theory technique that you've mentioned is primarily coming from like an expressivity angle?
Yes.
So can you maybe, I don't know, say like what, I imagine you have something in mind that like we couldn't do with the deep sets.
Please remember to use your seat microphone.
Sorry.
Like, can you maybe just shed a little bit more intuition about what kinds of things that we could do with this additional function that we couldn't accomplish just using those deep sets?
Sure. So, well, I don't have any specific example, but this group is much larger than this group. So the field of invariant functions is smaller, and there's a notion of degree that you can use for the degree of the polynomials that you need, or like the order of the group here is like pretty large. It's like n squared as a subgroup. So the size of these objects are quite different. So there's a significant space of functions that you cannot express. So for instance, I think that you can actually, for counting triangles is something that will probably show up as something that you cannot do here, but you can do here. So because you can modify this f star to be the product of xij, xjk, and that object is in this field, but it's not in this field. So that is one example of a function that will be here, but not here. Yeah. I will need to check exactly if that one is a function that is not there, but the counting triangles, I will need to check exactly that's what it does. Okay. So I promised you that I was going to do this with all of n times d features, but this is all of n squared still because I'm using all the off-diagonal elements. There is an extension that we can do to this that reduces the number of features that one needs to all of n times d using ideas from low-rank matrix completion. The idea is the following. So the matrix of inner products is a low-rank matrix. So you can reconstruct this matrix by looking at a small subset of that matrix. For instance, you can take a subset. So if this is a matrix of rank D here, well, the matrix of inner products, this one is a matrix of rank D, then I can recover it by observing D rows of this matrix genetically. However, if I observe D rows of these columns, then I need to keep track of the permutation symmetry. So something that you can do is to use some extra housekeeping data in order to be able to keep track of these permutations. So what you will do, and this is one way of doing it, is you can consider some centers, D centers, if your points are in dimension D. And these centers are going to be equivariant with respect to orthogonal transformations, and are going to be invariant with respect to permutations. So for instance, if this is my point cloud, I can take two centers, and this coming from, like, I don't know, k-means clustering for k equals 2. And these are equivariant with respect to orthogonal transformations. And you can think of them as, you can order them by norm, for instance, and they will be invariant with respect to permutations. And if you add those to your data, and you look at the graph matrix of this extended data, then you can use, say, these columns, and just these D columns would be able to recover the entire matrix, and you can use that for your machine learning model. So you can recover the entire matrix from, say, this part of your matrix, and then your model would be a deep set of the inner products of your points to your centers and the centers inner product with themselves. And this machine learning model depends on n times D features and is permutation is invariant with respect to permutations and orthogonal transformations. And the same thing holds using the ideas from the Galois theory that we saw before, since this is equivalent to the things that you can express with this Galois theory formulation, because you can reconstruct the entire thing. You can prove that this machine learning model can universally approximate invariant functions on point clouds outside this like bad set that is invariant closed and measure 0. So that gives a way of defining machine learning models on point clouds using ideas from Galois theory and low-rank matrix completion. So that's another example where we use algebraic techniques for machine learning. And finally, for the last part of my talk, I want to talk about using ideas that were inspired by work that was done in representation stability to define machine learning models or analyze machine learning models that have this property of being able to be evaluated on objects of different sizes. So the graph neural networks were one example, and also the machine learning models on point clouds using deep sets was that also satisfied that property. And good. Okay. So so certain machine learning models have this property that you have a fixed set of parameters, and that defines a machine learning model that can be evaluated on inputs of any size. One example is the graph neural networks, and the other example that we saw is the deep sets. And also the machine learning on point clouds that I defined in the previous slide. So the question is, what are the underlying mathematical assumptions that one makes when one defines machine learning models on varying size objects? What are the assumptions that we make, and how one can design these models so that they satisfy the properties that you want? So there's a lot of theory about this by people in the audience. Luana and Juan and Alejandro have very nice work explaining GNN transferability. the idea is that you can consider a sequence of graphs. Then this sequence of graphs may converge to a graphon, which is an infinite object, and which is like kind of like the limit of finite graphs. And then if your graph neural network satisfies your graph neural network satisfies that it can be evaluated on graph of any size, and also satisfies that it can be evaluated at the graphon limit. And so transferability, which tells you that you can train a graph neural network on small graphs, and that generalizes to large graphs, comes from the fact that these models are continuous. Like if you have a sequence of graphs converging to a graphon, then the sequence of the evaluation of this graph neural network on these graphs converges to the evaluation of the infinite graph neural network in the graphon. And so since you have convergence, then in particular, this is a Cauchy sequence. And so you can approximate the value of your function in large graphs by looking at smaller graphs, because this limit goes to 0. So basically, that's the main idea behind transferability. And maybe if you disagree, let me know. But in a nutshell, what happens is that the reason why we can generalize to objects of larger size is because we have a sequence of families, a family of functions that in the limit, they converge to a well-defined object, and this object is continuous. So mathematically, one can formalize it in the following way. So you have a sequence of input spaces, vector spaces. So you can think of these as inputs of size n, inputs inside of size n plus 1, n plus 2, etc. And then your machine learning model has a finite set of parameters, but it defines a sequence of functions that are defined in each of these spaces. And in many cases, we have a group acting in each of these spaces, in each of these input spaces. So for instance, in the case of graph neural networks, we have the group of permutations acting by permuting rows and columns in each of these spaces. And these groups grow with the size of the input. And we have in a limiting space, which is, you can think of it as the direct limit of all these spaces. And in this space, you also have your machine learning model defined here, and then this model is the limit of the models of the finite dimensional space. So in order to do that, you need to have these embeddings that tell you how to see objects of size n inside objects of n plus 1, inside objects of size n plus 2, and so on. So these phi's are embeddings. And then in that sense, you can define an infinite object that includes all the finite dimensional objects as well as inside it. All these finite dimensional objects are identified with some infinite objects inside this space. And so that will give you a metric to see if these embeddings are isometries with respect to the metric in each of these spaces. That will give you a metric in the infinite dimensional space that you can use to compare objects of different sizes. And so the conditions that we need are compatibility, which is that this diagram commutes. So applying the embedding and then applying the model is the same as applying the model and then applying the embedding in the output space. That's the compatibility condition. Then there is a space identification assumption, which is that these phi n's are isometric embeddings that allow you to identify objects of size n inside objects of size n plus 1. This doesn't need to be a linear order. It could be like something more complicated, but just for simplicity. Yes. You had a question? OK, sorry. And then you have a limit space where you can see that the direct limit of these vector spaces And in this space, you can quotient by the group action, and then you can consider the completion that we can discuss later. And then the transferability is given by these continuities, the continuity of this model. So the limit when n goes to infinity is f infinity, which is the model at the limit. And these are all continuous. And the choice of topology here is important, because in the finite dimensional spaces, all the topologies are equivalent, but in the infinite dimensional space, well, at least like if they come from norms, they are equivalent. And in the infinite dimensional space, they are not. So the choice of topology is important. And this choice of topology is going to tell you what models are good for your task and what models are not good for your task. And so how does this connect with representation stability? So representation stability tells you that if you have a sequence of representations by a finite group, like say the permutation group, then that sequence stabilizes in dimension. So the dimension of the space of linear functions that satisfy the equivariance is finite. The dimension is finite. Up to a certain point, it doesn't grow anymore, even if the input grows. So that tells you that you can parameterize all, all linear equivariant functions with a fixed set of parameters independently of the size of the input. So say, for example, say you have matrices, and you have the action of permutations permuting rows and columns. So the invariant functions with respect to that action are given by the trace and the sum of the entries. And that is independent of the size of your matrix. You only have two invariant functions with respect to that action. So the dimension of the space of linear invariant functions is finite for whatever sequence you have. And that tells you, the group here tells you that you can have a sufficiently expressive class of functions independently of the size of the input. So that's the reason why the group action makes sense here. But for this formulation, you don't actually need the group action. You can do it without the symmetric constraint. So you don't necessarily need it, but that gives you something that is useful. So let me give you an example. So if you have sets, so one of the questions is like, how do you see an object inside a larger object? And there are many choices that you can make. So for instance, for sets, one way of making your sets grow is by zero padding, by adding like zeros after you have your set, you copy your set, and then you add zeros. And then that is one possible set of embeddings that you can consider. And for that one, if you look at the limit space, you get infinite sequences with finitely many non-zeros. And then you can complete the two infinite sequences. Or you can design another way of growing your sets, which is duplicating. So if I have this set with these three things, then I can see it inside this set, where it's not really a set, but a multiset that copies the set twice, and then you can copy it 4 times, and so on. And that gives you a way of growing your sets. And by choosing how your objects are supposed to grow, you have knowledge of what is the metric that you need to use to compare them, because the distance in the infinite space, the distance between this and that should be 0, because these are identified by this consistent sequence. And so, for instance, in this case, your limit space is the probability measures with the Wasserstein P metric. And so you have different models, like the deep sets that I defined before. You can also normalize these deep sets by dividing by the number of points that you're averaging over, or the point net that replaces the sum with a max. And all these 3 models have are equivalent maybe in a finite space, but they are not equivalent in the sense of how generalized to larger objects. So that's the thing. And so for different models and different, say, ways you identify larger objects and smaller objects, you have you can check whether they satisfy the conditions. So for instance, the deep set is compatible and transferable for the zero padding, but is non-compatible for the duplication model. But the deep set normalized is compatible for the duplication model. So given, like, if you think of, like, how are my sets supposed to grow for these applications? So say if I'm sampling points from a manifold, how are my sets supposed to grow? And then what is the limit object that I can think of? And so what is the right model so that I generalize to objects of larger sizes? So that gives you, like, that kind of idea. How do you do this? So what we do with this is we are able to modify existing equivariant architectures or existing architectures to make them transferable. So for instance, we can look at different GNNs or machine learning models and point clouds and so on, and make them transferable with respect to the conditions of my problem. So how are my objects supposed to grow? So what are the consistent sequences? What is the task? The underlying task that I need to learn needs to be expressible by these models. I need to be continuous with respect to the topology that I get in the limit. So my task, so I need to choose a topology that makes my task continuous, or that my task is continuous under. So this gives you a recipe to understand the conditions between the task, the topology, and the model that I use. And you can recover theoretical results like generalization bounds and so on that I'm not going to discuss now. And yes.
So I was thinking about maybe the simplest case. I just have a one-dimensional curve, and I sample it, and I want to double the sampling and triple the sampling. Mm-hmm. So when going up, maybe doing linear interpolation or some more sophisticated way of interpolation might be a better way of growing the space. So I was curious as to why zero padding or duplication might be adequate, or did I misunderstand the role of?
So the role of the zero padding or duplication is you're asking what objects do you see them as the same. So in your specific example, I will say that the duplication is the one that you want, because you have 3 points in a curve, and if you have the same 3 points in this curve twice, then they represent the same curve. So if I sample the 3 points and I sample 6 points, but these points are repeated, then in my machine learning model should identify these two things and just give them the same value. So these embeddings just tell you what things should be equivalent, because your machine learning model is going to have to identify some things because it's going to be defined in a finite set of parameters. So it needs to identify things that to do the same computation. And graph neural networks also do that. Mm-hmm. Did that answer your question? Yeah, great. So these are just numerical illustrations that show you different models and whether they are compatible or transferable. I think in the interest of time, if you're interested in this kind of discussion, you can go to Yuxin's poster, and she can explain you what these curves mean. And finally, I'm going to show you an application of these ideas to learning PDEs. So the idea is the following. I'm just going to give you a simple example of how you can apply this like any-dimensional learning for learning PDEs. So say that I have some data that satisfies PDE, and my goal is to learn this PDE from the data. So I want to learn the equation from the data. Like Maybe not in a symbolic way, but I just want to learn this function. So I want to learn this function in a way that is coordinate-free and dimension-free. And I want to make it be able to generalize to other domains with other dimensions and other initial conditions. For example, I can have the heat equation written like this. And so the du dt is equal to the Laplacian of u. The Laplacian is an operator that is defined for any manifold, Riemannian manifold. So if I change my manifold, my domain, I know that what I should be using is the Laplacian. So there is like writing the Laplacian is something that I can write in a way that is coordinate-free, because the Laplacian is intrinsic to the manifold, and dimension-free, because you can write the same equation for any manifold. So for instance, in this example, I have several scalar fields, and I have the PDE given by these functions of these scalar fields. And if I consider that these equations that they satisfy are orthogonally symmetric second-order PDEs, and I want to learn this from data, then we can show that these functions, FIs, needs to be functions of the scalar fields, the Laplacians, and the inner products of the gradients of the fields. And this gives me a basis for all the orthogonally symmetric second-order PDEs. And then I can learn my PDE in this basis. And if I change the manifold, the different manifolds would give you different basis elements. But the function that I learn is here. So the function that I learn can generalize to other manifolds. Does that make sense? And so we have some illustrations where we learn some differential equations in dimension 1 and then generalize to other dimensions with other geometries. So the function that you learn is how do you transform your basis elements into a PDE, and then you can use the same function, the same neural network weights, evaluate on the corresponding basis of the other manifold, and that will give you the corresponding PDE in a different domain. So the question that we want to ask is, what are the assumptions that we're making when we are doing this? And can we use this, for instance, for learning PDEs or learning how to solve PDEs? Or can we use this for sampling and for diffusion problems? And what kind of any-dimensional generalization you get by using this model for PDEs? Of course, you cannot do anything. There will be a specific set of rules of what are the things that you can generalize to by using these. But maybe there's a way to scale these bases in a different way, and then we'll generalize to something else. So that's kind of what this theory allows you to study. And here there's another example where we learn PDE in dimension 1, and we generalize to other coordinate systems and other manifolds as well. So I have a few minutes left, so I just want to summarize some ideas from algebra that we use applied to machine learning models. We use classical invariant theory to design equivariant self-supervised learning. We use Galois theory to design invariant functions on point clouds. And we use ideas from low-rank matrix completion to make them information theoretically optimal. And we gave a theoretical framework for machine learning models on varying size objects that study how the growing of the objects in size connect the task, the topology, and the model. We have an application to PDEs, and I'm happy to talk about that offline if you're interested.